Good evening
Yes, sir,
and
you are audible, sir.
uh, good evening and welcome to week 12 of the live interactive session of the Neural Science for Engineers. The course instructor is Professor Vikas V from NIMS Bangalore, and I am the PMR of Teaching Assistant Vikas from IIT Jodhpur. This is a brief about me, and this is the YouTube channel where you will find all the recording of the discussions we do. So, as we have been doing from the previous few classes, that we will first discuss the summary of the week and then we will go into the questions. Okay, so like in this week we have mainly seen the micro engineering for neural science acquisition. That means how we are creating the small devices that we have like we studied about stimulating signals and all. So how we are creating such devices from which we are able to take out the signal from our neurons or from our brain. Specifically, if we say there are some different type of neural signal acquisition techniques, like one of most common one is the ECG. ECG is for heart, right? So electrocardiogram, that is also a way of measuring the biopotential. EMG, that is the electromyogram. EEG, that is for brain electroencephalogram. MEG, that is magnetoencephalography. All these measure biopotential, or we can say, as we have seen, all the biopotentials are in terms of the gradient or the potential that we have, that is in terms of ions. So, ionic potential we are measuring, and that in the form of electrical outputs. Okay, so one of the most common one for neural science is EEG, that is uh, that have very small voltage, and since the skull itself in this we are not getting inside the brain. Electrodes are put on the surface of the brain, that is on the skull and outer surface. So it has lower voltage due to skull impedance, and it is fine for the temporal signals are fine, but spatially it is not that uh, well, not a very good technique, because we are not able to reach to specific areas of the brain uh, where we want to find the signal. So these techniques we can divide into three sections, we can say. That is, first one is non-invasive techniques like EEG and MEG, where we are not getting inside the body. The things are being done from the surface. Then second one is minimally invasive techniques like ECOG and SEEG, that is in which small cuts or small incision can be made, but not uh, too much. Then are invasive techniques where some implants are being done. So ECOG may be minimally invasive, or in some cases it can be fully invasive also, as well as SEEG and intracortical implants. So what are the benefits or the limitations of invasive neuropotential acquisition? The benefit is certainly, like I said, we'll have a increased amplitude of biopotential. There is no barrier, no impedance. So there is no barrier, no impedance. So we are directly getting the signal. Certainly, it will have um, good amplitude. We will be able to find in a better frequency. There will be no delay. Improved signal to noise ratio. That means we will have lesser interference or lesser noise, and we will be able to easily map the function of the brain. We can pinpoint to our specific areas. The limitation is limited recording time, since the brain is such a sensitive part that it cannot be kept open, or uh, an incision cannot be kept for a longer period of time. as well as there is a limited area of consideration. We have to be very precise where we want our electrodes to be put. Then is risk of damage, cerebrospinal fluid leakage, which is a very critical thing, bleeding, infection. So in all this, uh, microengineering plays a role. That is, uh, microelectrode arrays for surface brain signals. These are developed by microengineering. As we have seen previously also how flexible electrodes are needed, they must be biocompatible and these things. But here we are not talking about stimulation, we are talking about signal acquisition. In this case also, uh, microengineering or microfabrication plays a role in creating the microelectrodes. Then there is something called as bioresorbable ECOG electrodes. That means they don't need to be taken out. If we are putting some invasive, using some invasive technique and we are putting an electrode, such an electrode which say after some time it will just decompose or it will mix up with the tissues, and it is not going to cause any problem, and so another surgery to take it out is not needed. Then second one, as we have seen, flexible electrodes for epilepsy detection in these things. Fine till here? Any questions or confusions? Okay.
No, sir, no questions.
Okay. So let's move to some fabrication techniques. Though fabrication techniques are like fabrication technique means microfabrication techniques. Okay. So this itself is a very vast field. In fact, a field that one single technique of a microfabrication technique can yield into a PhD. Okay, so this itself is a very vast field. There are different if someone is interested in it, it is a uh, like there are different lectures, different courses over it. But let's make a brief of it and understand it. So ideally, to make an electrode, two things are to be done. One thing is deposition, and the second is patterning. Since we cannot have, since we are trying to make very small electrodes or very small objects, so what we have to do is that we want precise deposition of layers of maybe metal or our desired film. Okay, and we want to pattern it. So we will just be discussing these two, though there are many steps before this, steps after this, including cleaning and a lot of things. But mainly in this week, two things has been discussed. That is deposition and patterning. So deposition technique, uh, roughly we can divide it to two: physical vapor deposition and chemical vapor deposition. Physical vapor deposition, where no chemical reaction is taking place, but the material itself is changing the phase and going and being deposited. Like we have a crucible. Suppose in this we are putting, say, gold, and we are hitting it electrically, very high voltage. Say, uh, like in thermal evaporation, generally we go till 100 or 150 amperes at 440 volt. So you can understand how much power it is. So so high power that it melts it and it evaporates the gold, and then we have our substrate on the top and it gets deposited. Here the phase is changing but gold remains gold. If we are going for silver, titanium, chromium, any such thing, in all the physical vapor deposition techniques, the phase changes but the material remains the same, including the sputtering technique. Okay, so there are mainly three major type of physical vapor deposition, that is thermal evaporation, electron beam evaporation, and sputtering. Okay. Then there is something called as chemical vapor deposition or CVD. So anyone from electronics background? Yeah, I think Sajid, you
Yes,
are
sir.
from electronics, right?
No, sir. Actually,
Oh,
I'm from Aero.
okay. Yes.
So I'm from instrumentation.
Okay. So a bit of electronics, I think you might be knowing.
Yes, sir.
So are you aware of this PVD, CVD techniques or all?
No, sir.
No. Okay. These are mostly covered in masters, generally, masters and all. I think in bachelor's, they are not doing the microfabrication and all. Okay. So I will be giving a brief, and for details, I think there is one course by Hardik sir only, who has taken the this week's lecture. Okay, you can find on NPTEL. Okay, so CVD techniques, simply put, there are some chemical reactions taking place. Okay, the deposition is there, but the deposition occurs due to the reaction of two or three species, or we call it as precursors. Okay, so there are different type of CVD, like atmospheric pressure chemical vapor deposition. So there is no low pressure being done, and when we are not going for any pressure change, that means there will be contamination. There will be dust particles, and these things can get inside. So this is the simplest one, but not good quality, you can say. Then is low pressure chemical vapor deposition. Then is plasma enhanced chemical vapor deposition. So we are mixing plasma with CVD. Then is high density plasma chemical vapor deposition. So plasma intensity is increased. Then there is something called atomic layer deposition. So layer by layer, atom by atom deposition takes place. This is also a CVD technique. They are also precursor output. Okay. So how do we differentiate between these two? Okay. So physical vapor deposition used to produce the constituent atom that condense on the vapor. So we can say only the phase changes. If it is solid, it will go into uh, a gaseous form, and it will uh, condense. If it is in liquid phase, it will go into gaseous phase and condense. Okay, or it can either go into plasma phase and then condense on the surface of our target material. Okay, there can mostly evaporation is one very common way of doing this, but evaporation in a very high vacuum chamber, so that there is nothing else, and that's how we can get good sublimation or evaporation of the materials. Okay. Then second way is sputter deposition, where it is bombarded. If we think of something like if we have a pool of uh, what we say, mm, if we have a pool not of water, like muddy water, okay, or mud, we can say a pool of mud, and if we throw a stone over it, what happens is that since the stone has some momentum, it will hit it, and this will result into the mud getting sputtered towards outside, right? So using this technique only, but here uh, the bombarding particle is generally argon. Okay, argon ions, argon plasma is used to bombard it and take out molecules and get deposited over the material. So as the name suggests, the evaporation will be at a higher temperature. Sputtering will be at a lower temperature, though it can also be done at higher temperature for good adhesion and these things. Sputtering is mostly used for metal and alloy deposition. Okay, not sputtering. Sorry, I'm saying evaporation and sputtering both. I'm saying PVD. These are generally for alloy and metal deposition. Metal alloys are most common ones. Okay. Then comes chemical vapor deposition. I will show in details also. In CVD reactant gases are introduced into the chamber. So mostly the reaction here takes place in gaseous form. Though the precursor can be solid or liquid, the reaction will take in gaseous form. Then the reaction of gases takes place on the wafer surface, resulting into layer deposition. So 2-3 species are coming, and these reactions are happening on the target where we have to deposit, and there this deposition occurs. And how do we ensure this? This we ensure by knowing the temperature of reaction. At what temperature this reaction will take place. Okay, so that is made in a furnace. So this is also a high temperature process. In this case, some low pressure technique, not the APCVD, but low pressure techniques are used to deposit silicon, silicon dioxide, polysilicon, and silicon nitride films. Even silicon nitride can be deposited using physical vapor deposition, but it cannot be made. We will have to have the target having silicon nitride or SiO2 to deposit using sputtering. But in case of chemical vapor deposition, we can have silane and other constituent elements, and that reaction will take place and it can be done. Okay. So as I said, we will be discussing mostly deposition and patterning. So patterning is done using a technique called as lithography, which we will see a bit later. Okay. So evaporation source can one be through current, high current. Okay. The second option that is a better way is using electron beam. So it is e-beam evaporation or electron beam evaporation. They have different type of evaporation sources, like you must have seen in the lecture, that is having single pocket, rotary pocket, or a linear pocket. So uh, single pocket or single crucible where electron beam is directed and it will evaporate that, or rotary pocket where the electron beam's position is fixed but the crucible or the pocket moves. Then is linear pocket where the pocket is the electron beam is linearly focused over different pockets. Okay, these sources, like many a times you must have heard that though we seeing the electrodes, you might feel like there is gold over it or something, but it is not a single layer. It can have multiple layers like chromium, titanium, gold, nickel, gold, based on our uses. Okay, to have a good ohmic contact, we might need different layers. Okay, so such sequential deposition cannot be done one by one, because if you take that out from this high vacuum, it will oxidize and we will not get continuous layers. Okay, so such sequential depositions are needed, and that also in one go, and that can be done using single pocket and rotary pocket or linear pocket. Okay, how the thickness is measured in this case, that is done using quartz crystal monitor. There is a quartz crystal monitor that on which this same material that is being deposited over our sample is also getting deposited over there, and the mass of it changes. As the mass changes, the oscillating frequency changes, and thus the film thickness is measured using this. Okay, so let's see what is sputtering process and chemical vapor deposition simply. So sputtering can be uh, either thermal, we saw it is directly DC based or electron beam based. Sputtering can be again DC sputtering, radio frequency sputtering, magnetron sputtering, or reactive ion sputtering. Okay. The concept is, uh, if you see just the concept wise, it is that the sputtering gas, that is mostly argon, gets inside this chamber, and that also at a very low concentration, not very high. Generally, we take something in the range of 10 to the power minus 2 millibar. So if you say 2 or 3, 3 into 10 to the power minus 2 millibar. So this is very low concentration of argon gases put inside it. This is our target. So let's say silicon dioxide is set. Okay, this argon will come, and a plasma is formed between these two using either DC sputtering. If it is DC sputtering, the DC source using cathode anode. If it is RF, we will put radio frequency. Like that, we will create plasma. When the plasma is made, this argon will convert into argon positive with very high energy, and it will hit this sputtering target. Once it hits, it will take up, since argon is a heavy material, heavy atom, we can say, it will hit it with some momentum, and it will remove the molecules, and that molecules will travel towards the target, depositing it, and this target is kept moving, rotating. Okay, this is a simple way how sputtering occurs. Then is chemical vapor deposition. This is a process in which gaseous precursors react to form a solid coating on a heated substrate. So it's not this small, it is a big zone, like 3 zones are there. So we are considering the zone, let's say this is the zone 2, where our reaction is ideally to take place, say 850 degree or something like that. Okay, so gases are inserted, precursors are also put in crucible. Okay, so these gases will carry, since it is so hot, this area will also get hot. It will carry these constituent elements, and as it will reach this part, the surface will act as a place where these two or three spaces will meet, and they will react, and the byproducts, uh, whatever we want, that will get deposited there, since it will be in solid form, and the byproduct will leave the this furnace. Okay, so this is the basic process of CVD. Fine till here? Any questions?
No, sir.
No, sir.
Okay, now comes the lithography, which is a very important part in case of any microfabrication technique. Okay, lithography, simply said, is a way of patterning. Okay, and there are, just a minute. Hello, can we continue?
Yes, sir. Yes, sir.
Okay. So, the next technique, that is a very crucial technique, that is lithography. It is one of the most important and crucial part of microfabrication. If you talk about microfabrication techniques are mostly used in processor and these things. Okay, if you talk about that, 80% of the cost of fabrication of processors and microcontroller, they come from the technique that is lithography. Okay, it has a very crucial role, and if we put the literal meaning, it is litho means stone, and graphy, that is carving stone and this thing. So here we are using something called as photoresist. It is a simple, if you think of it as a stencil kind of technique, where if you have to draw something and you are putting a stencil and you are putting the paint all over it and then removing the stencil, the pattern will be there, right? It is the miniaturized form of it, you can say it. But since we are dealing with dimensions in micro and nanometer, yes, Sajiji, you are saying something. Hello. Okay. So
Yes, sir. Yes, sir. Continue, sir.
yeah. So here something that is called as photoresist is being used. Photoresist means a resistive material or a resin that is photosensitive, that changes its chemical composition or structural formation based on the exposed light. There are two type of photoresist, that is positive and negative. The positive one, the area that gets exposed to light will become uh, soluble in a compound or a liquid called as developer. In case of negative photoresist, it is just the opposite. The exposed area will remain stable. Unexposed area will be uh, soluble, like that will become soluble in the developer. Okay. It is a technique used for fabricating microneedles and flexible microelectrode array. The steps include coating, patterning, and etching. So, steps we'll see first. Let's be clear with the mask. Mask is the pattern. Okay, so it is something like suppose that uh, am I visible? My video is on, right? Suppose that this is something on which we want to create a pattern. Okay, then we will take a uh, glass structure which will have the pattern. Let me draw over here. Okay, so this is a blank wafer, we can say, on which we want to put a pattern. Okay, then the pattern we will have on a glass, and on this glass, suppose the pattern is made like this. Okay. So this is made of glass or transparent, we can say, and the pattern over it is made up of chrome, that is opaque. Okay, now to start with, there are two type of photoresist, that is positive and negative, that is clear. Then there are two type of mask also. One is bright field, like the one I have shown, where only the pattern is dark, other areas are open. This is bright field. The opposite of it, where all the areas are dark and only the pattern is having nothing, like transparent, that is a dark field mask. Fine. This is a point where almost everyone gets confused. Which one is positive, which one is negative? What happens in case of positive? What happens in case of negative? What is bright field and dark field? But once you will be clear about it, you will be able to understand how this process occurs. Okay. So based on this, if we put, say, this is our mask, this is our wafer, this is mask. Okay. So what happens is that we will take the wafer, we will put photoresist. Photoresist is liquid in form. We will put the photoresist and spin it at a very high speed. Okay. At when we spin it at high speed, what will happen? Anyone? Am I audible?
Yes, sir. Yes, sir.
Okay. So if we put a liquid over a flat surface and spin the surface very fast, what will happen?
Water will form. Water center from center. It will go to away from the center.
Center and
Spreading.
spread. Yeah, if very thin layer of this liquid will spread over it. This is a viscous liquid, not very, you can say not very watery. It is a bit viscous. Okay. So a thin layer of this photoresist forms over it. Then we take it, like we just dry it a bit so that it solidifies, but it does not stabilize. Okay. Then we take it into our lithography system. We put it. Then we put the mask over it. Okay, the mask that is having our patterns, and we will bring these two together, like very close to each other, and we'll put ultraviolet light from over it. There are different techniques like in some techniques electron beam is also used, but simplest one is photolithography, that is where ultraviolet light of fixed uh, wavelength, that is 365 nanometer or 405 nanometer, is used to expose it. Once exposed, we will remove it, and then we will put it to developer, and we will see that pattern is there. And the pattern will depend on two things: whether our mask was bright field or dark field, and our resist was positive or negative. Okay, so if the mask is bright field, I am putting BF for bright field and DF for dark field, and this resist is positive. Okay, positive resist means which area will get dissolved, the one that is exposed or the one that is not exposed. Yes, yes, are you there?
Yes, sir.
So in
Yes,
case
sir.
of positive, which area will get dissolved?
Sir, not exposed.
Not exposed area will get dissolved. No, in case of positive, the exposed area gets dissolved. Fine.
Okay.
So what happens is that you see uh, this area, the black area that is having the light here, right? The one shaded area that will not get the light in this case. Okay, the dark one that is getting the light. Okay, and the next when you will develop, this will go out, and only our pattern will remain, the dark pattern. Opposite in case of dark field with same photoresist, since this area is getting exposed here, this area gets removed. Okay, same type of mask, but opposite type of photoresist, that will give us the opposite patterns. Fine. Once we have this pattern of photoresist over it, then below it we have something like gold, silver, and other particles. We will put it into etchant like gold etchant, silver etchant, or aluminum etchant, whatever we need. Okay. So what will happen is that since this area is protected, okay, so all other areas, the gold or metal will get removed, and only this area will remain. And then at last we will put this whole wafer into acetone, that will remove the PR, since the photoresist is not of our use. It was just there to make the pattern. It will remove the photoresist, and we will get the pattern of our metal. Fine. There is one more technique. Some techniques like this dark field mask. What we were making from this dark field mask, right? The area that we want is uh, open. Other areas are covered with photoresist. In this case, metal is deposited later on. We have this mask, we will take it, and then we will deposit using PVD techniques. Mostly CVD will not sustain in CVD mostly generally. So not even in case of thermal, it will be mostly suitable in case of sputtering and these techniques. So uh, it will be deposited over it, and then we will put in acetone. So what will happen is that acetone removes this PR. So when it is getting removed, it will take out all the metal deposited over it. But the area where this PR was not there, the metal will remain there. So the final structure is the same in both the cases. It is just the technique will differ. One technique, that is where we are lifting off later on. So in that case, metal we are depositing later. In another technique, the metal is already deposited, and that we are patterning using the etching technique. So it depends on our use case, as well as sometimes like some materials are very hard to etch, like palladium and platinum. In that case, lift off is used, but it is a bit delicate, you can say, uh, to do lift off compared to normal etching process. But yes, where we don't have etchant or We have to go to very smaller dimensions. Lift-off is the way. Fine. Any questions still here? Or any confusion?
No, sir. We'll go ahead, sir.
Good. Okay. So one more part is covered in this week lecture that will cover day after tomorrow. Okay. Like I said, there will be one more class, right? So since this lecture becomes very big, we will be covering that part in the next class. Okay. So let's start with our problems. Okay. What does EEG stands for? Electrocardiogram, electromyogram, electroencephalogram, electromagnetogram.
Electroencephalogram.
Electroencephalogram. That is C, right? So
Yes,
it
sir.
measures the electrical activities in the brain. And this is a non-invasive technique. What is the main advantage of invasive neuropotential acquisition? Decreased signal to noise ratio, limited recording time, increased biopotential amplitude and frequency, reduced risk of tissue damage.
Increased biopotential amplitude and
Amplitude and frequency. Fine. And it will not be decreased signal to noise ratio, it will be actually increased signal to noise ratio as it improves signal quality. Fine. Which techniques involves dislodging atoms using argon plasma? Thermal evaporation, electron beam evaporation, sputtering, or chemical vapor deposition?
sputtering.
Sputtering. Fine. Fine till here. What is the
Yes, sir. Yes.
what is the advantage of bioresourceable electrodes over biocompatible ones? We have learned about biocompatible ones earlier, right? That it should not be attacked by our immune system. Now we have talked about bioresorbable electrodes. So what is the advantage of bioresorbable electrodes over biocompatible? Longer recording time, lower cost, compatible with the human body, dissolution inside the body.
Sir, D.
That is dissolution inside the body. And what advantage it will give us?
So we do not have to remove it later on.
Yeah, so we will not need to do the removal surgery. Okay, so eliminating the need of removal surgery. Which technique involves physically evaporating and depositing the material onto the substrate? Chemical vapor deposition, sputtering, physical vapor deposition, or electron beam evaporation?
So PVD.
PVD, okay. So, any other answers?
Sir, D also same only. Electron beam
Yes, sir.
evaporation.
Yeah, it is asking physically evaporating and depositing. In case of PVD includes both sputtering and uh, thermal evaporation and electron beam evaporation. Okay. In case of sputtering, we are not evaporating. We are using the argon plasma, right? So PVD will be a partially correct answer,
Yeah, okay, sir. D will.
right? It will be electron beam evaporation or thermal evaporation. That is part of PVD. Fine. So we must know the difference. Okay, no, I have this one is wrong. It is this one. By mistake, I have marked. Right? It is electron beam evaporation, not PVD. Okay, I'll correct this. What is the main limitation of invasive neuropotential acquisition? Here we are talking about limitation. Okay, decreased signal to noise ratio, limited recording time, increased risk of tissue damage, reduced complexity.
Sir, it is C. Increased risk of tissue damage.
Tissue damage, since we are getting inside the brain. Okay, whereas in case of non-invasive methods, there is less chance of tissue damage. Which techniques involves hitting a material on a source holder until it evaporates. Electron beam evaporation is sputtering, chemical vapor deposition, or thermal evaporation.
So thermal evaporation.
Thermal evaporation. So this is a bit again different than electron beam evaporation. Here, the material is being heated till it evaporates, and there, in case of electron beam, it is being hit by electron beam. This is also being heated, but the technique gets different. Okay. What does CVD stands for? Continuous vapor deposition, chemical vapor deposition, condensed vapor deposition, or coated vapor deposition?
Chemical.
Chemical vapor deposition. Recently, I came to know that this new phones, iPhone, the newest version, I think it's 15 or 16, the latest one. Yes, must be knowing.
So 15.
15, yeah. That is having some titanium coating, right?
Yes, sir.
Yeah, that is being deposited using some plasma enhanced CVD. If you read that, you will find that it is being deposited using plasma enhanced CVD and such techniques. Okay, so these techniques are very commonly used in electronic industry, though it might not sound familiar to common people, but it's a very common technique. Okay, what is the primary purpose of microelectrode array in neural signal acquisition? Record signal from muscles, mapping brain functionality, diagnosing heart condition, enhancing signal to noise ratio.
So B.
B. Mapping brain functionality. Any other answers?
I think muscles recording is also maybe going with this.
When we are talking about neural signals, so muscle also have signals, but that is not of much interest if we are getting into like certainly we can record from muscles also, right? And in fact, myocardial muscles also have signals that are recorded. But in case of neural signal acquisition, it is mostly about brain
Brain.
functionality. Like we now you must be able to appreciate why we read about the anatomy of brain and what are the connections of brain and these things. Because as we saw that there are different pathway for input and output, right? What pathways are there and all. So putting these electrodes in that path, we can understand that whether the signal is being conducted or not and these things. So understanding the brain properly was needed so that we can uh, map these functions very properly. What problem is occurring there and these things. Okay, that might have sounded like why we are getting into brain too much, right? We were talking about neuroscience for engineers, right? So we should have talked about devices directly. But the use of these devices will be very clear only when we are aware of the neural structures, how they occur, what potential is being generated, and in what case, if this one link is broken, what might be the problem? Like someone is having problem with eye, so what link might be broken, and these things we have to understand, and that can only be done when we have a complete knowledge about the brain structure and brain working. Okay, what is the primary limitations in case of PVD compared to CVD? Poor surface coverage, limited material option, inability to deposit dielectrics, or high process complexity.
So A. Poor surface coverage.
Surface coverage. Okay, any other answers? More than one answer can also be correct. PVD, when we are talking about, it includes sputtering, thermal, and E-beam, right? All three of them are covered inside PVD.
Poor surface coverage only, no?
Yes, it is poor surface coverage due to the one effect known as shadowing effect. And this can be mostly this is achieved by either rotating the substrate or such methods, or doing it into pulses, pulsed laser deposition, pulsed laser ablation. These are techniques that are now being developed, that are uh, being used to increase the surface coverage. And in fact, when you do sputtering and check, the thickness will vary in the central part of this wafer. You will get different thickness, and sides it will be different. So there, like, a lot of trial and error have to done to get like minimal error, uniform film and these things before this installation is done, and then it is checked. Okay, so surface coverage in one is one issue, but one advantage also is there. In case of CVD, very high temperature is there. Once you have already made some pattern or deposited, then later on CVD is difficult to be done over it. Okay. So which technique is preferred for PVD materials with high melting points? In case of PVD, especially in case of evaporation methods, we have to melt it, right? So in case it has very high melting points, so should we go for thermal evaporation, electron beam evaporation, or chemical vapor deposition or sputtering?
So B, electron
B,
beam.
electron beam evaporation, as it generates sufficient heat to evaporate them. Okay. Then, what is the role of shutter in case of E-beam evaporation? Controlling the electron beam, measuring film thickness, prevent deposition until the desired rate is achieved, seal the substrate from contamination. Yes, any answers?
Maybe C, prevent deposition until the desired rate is achieved.
In fact, a shutter is provided in case of sputtering also, so that we wait till the correct rate is achieved. Otherwise, we might not be able to understand what deposition occurred at the starting point. Okay, so we wait for the steady rate to be achieved, and then the shutter is opened, and then the deposition starts. So we have correct measurement. Okay. How is the film thickness measured during evaporation? Using X-ray diffractogram, by monitoring the electron beam with a quartz crystal monitor through surface topography analysis.
So C.
C, with a quartz crystal monitor. And why cannot we use D? This is to measure the thickness only, right? So why cannot we use D for this? Yes, any answers?
I don't know, sir.
Because this technique will need the sample to be taken out like this. Whole surface topography analysis cannot be done inside that. Um, you can say that evaporation chamber. Okay, quartz crystal monitor is not a very good way of measuring it, but yet it is the only thing that can be put inside this setup. Right? We cannot deposit some a bit and then take out and test it and then put it. Right. So later on, this X-ray diffractogram and surface topology are done. But while depositing, it is measured using quartz crystal monitor. Right? Which type of evaporation source allows for the sequential deposition of different materials? Single pocket, rotary pocket, linear pocket, or crucible?
Must be rotary pocket
Rotary pocket.
or linear. Both are maybe correct.
But rotary pocket is the best suitable way that allows sequential deposition of different materials. Linear pocket can also be used, but in that case, mostly alloy kind of things are easy to deposit. What is the primary advantage of electron beam evaporation in terms of contamination? As I have been saying that contamination, dust, and these are a problem. Okay, so what is the advantage that electron beam gives in case of contamination? Is it giving high deposition rate, low power consumption, reduced contamination level, or better step coverage?
I think that high deposition rate or reduced contamination.
Reduced contamination, because that is the question itself. Is it it in the question itself? The answer is it is having a reduced contamination level. What is the thickness? How is the thickness uniformity of deposital film described in electron beam evaporation? By cosine law, through X-ray diffractometer, through surface topography analysis, or by monitoring electron density? Yes, any answers?
So this monitoring electron density.
It is about uniformity,
Oh,
how
uniformity.
uniform film is.
No.
Monitoring that we have already.
The C.
X-ray.
X-ray
Oh,
will give the crystal uh, peaks, not the thickness. Uniformity will not be there. Surface topography will give us an average of it. Okay.
cosine law
Yes.
only. What is cosine law, sir?
Okay. You have not attended the lecture yet, it seems, right?
No, no, I attended in that cosine law. They are not saying.
Okay. It is described by cosine law. Okay. So this is defined by the angle between our target and the source. Okay, this same thing is being used in case of sputtering also. So uh, when you will see the sputtering system, the source and the target are not not at 90 degree, like not facing each other directly. They are having some angle. Gun, they are called as guns. Okay, so the target gun is kept at some angle, generally 45 or something. Okay, so that is due to the cosine law that will ensure the uniformity. Like I said, if it is kept directly, it will give us the highest thickness in the center and lowest around. So if we have at some angle and then the source, the substrate is moving, the the final substrate that on which we have to deposit, that is moving uniformly, that will give us uniform thickness. And this is determined by the cosine law. Since like if this is the target, not target, this is substrate and this is our target. So this this angle and this, this this angle will play a role. Okay, so if we see properly, actually it is based on cosine. What is the ratio cosine? It is base base and hypotenuse or perpendicular and hypotenuse.
So base and hypotenuse.
Base and hypotenuse. So in this case, what will be the base? If we are taking this angle, right? So this one will be base, right? And this
Yes,
one
sir.
will be hypotenuse. So this angle, since these two determine the angle, so it is defined by the cosine law. how well the uniformity will be there. Okay, it is just mentioned a bit, right? We don't need to get too much in details of it. It is done by cosine law. That's what does ECOG stand for? Electroencephalograph, electrocorticography, intracranial electroencephalogram, or electrocardiography.
So B.
B. That is electrocorticography. In this case, we are taking signals directly from brain. It can be minimally invasive and fully invasive also. Just a small bit of skull can be opened, or it might be done in case where we have to go deep into it. Right? What is the primary purpose of lithography in microfabrication? Coating the substrate, patterning material on the substrate, etching the substrate, removing photoresist from the substrate.
B.
B. Patterning materials on the substrate. Any other answers for this? Are we not coating the substrate in this?
That coating is not there, but etching the substrate is there. We are
Yes,
removing
we are
something.
doing, we are even coating the substrate with photoresist. We are
Right.
etching the substrate
Mm.
later on. We are even removing the photoresist. But all of this is being done for one
For
single purpose, for
patterning.
patterning. Yes. So all these are part of lithography, but patterning is something that our main purpose is. Fine. So don't get confused that okay, these steps were there in case of lithography. Okay. What is the property of positive photoresist? It creates patterns opposite to the mask, stronger in area exposed to UV light, requires higher temperature for processing, or forms thicker coatings.
Creates patterns opposite to the mask.
Yes, any other answers? Yes. Okay. It is stronger in areas exposed to UV light. It creates the pattern same as the mask.
Now, when you put a mask, for example, mask
Mhm.
has a hole, then
Yes,
whole post UV will be activated.
yes,
Then UV part will be removed as a positive thing.
yes.
Correct.
The
So
exposed, yeah.
so mask is the hole in the center. This also hole in the center.
No, no. This when we are talking about this pattern, no, that is not a hole. That is
For
covered.
example, I'm saying, for
Yeah.
example,
See,
there is a plate
if this
inside
is,
a one hole.
yeah, if this is the mask, let's suppose, okay, okay. So when we expose light over this for a positive photoresist, the this area will get stronger. That means get stiffer and will dissolve in the photoresist. Only the area that was not exposed to UV light
Uh, that
will
only will
remain.
remain. So
Will
mask can
remain.
be same.
Yeah,
Mask
it
and
will be
this pattern is same. That's what I'm
same.
saying.
Yeah, so it will create pattern same to the same as the mask, not
Okay,
opposite, right?
okay, okay.
So, and when we are saying stronger in area exposed to UV light, so it seems like it will remain, but stronger means it will get dissolved in the uh, developer,
Oh, okay.
the
Reverse.
chemical
Okay,
reaction that occurs. Fine. What is the purpose of spin coating in the photolithography process? Etching the substrate, applying a uniform film of photoresist, patterning the substrate, or removing excess material from the substrate.
B, maybe
So B.
applying.
Uniform film of photoresist. And one thing is that at what speed we rotate it, that will determine the thickness of our photoresist, how thick it is, and that will determine the dose of our exposure. So it has a very important role to play. If it is of say 1.5 micrometer, how much UV light has to be put, like UV light will be the same for how much time, so that it have to penetrate exactly till the end of this photoresist. There are something like if you put a lot of light, so it will start exposing this side also. Sides will be exposed, we will get pattern different than what we expected. In case we are not exposing it properly, so pattern like this will happen. So actually we will have photoresist throughout our surface. So this thickness and the dose, they have to be calibrated, properly optimized. Okay. So the purpose spin coating is to apply uniform film of photoresist. The rate will determine the thickness, right? Rate of spin will determine the thickness of photoresist, and this in turn will determine UV dose. Fine. So these are all interrelated. What does DRI stands for? Deep reactive ion etching, re direct reactive ion evaporation, diffusion reaction ion etching, double reactive ion evaporation. Yes, any answers?
Deep reactive ion
Deep
etching.
ion etching. So this is mainly used for creating deep features on the silicon substrate. This is a dry etching. Like we have not got deep into etching process. There is something called as wet etching, some is dry etching. Wet etching, in which you put that inside a chemical, wet chemical, and dry etching is something where you are doing using plasma mostly. Okay, so this is deep reactive ion etching. This is part of a dry etching process. What kind of signals are typically acquired using ECOG? Muscle activity signal, heart rate signal, brain activity signal, or respiratory signal?
C.
See, brain activity signal. Okay. Directly from the brain surface or even deep sometimes. What does ERP stands for in neural engineering? Electrical resistance potential, event-related potential, electroencephalographic response, or excitatory response patterns.
B. Event related.
Event-related potential. Okay, related to different stimuli. What is the purpose of pre-processing in ERP analysis?
I think this has to be covered in next lecture, no? ERP
Yeah,
business.
I am just giving one more question over this, and then we will continue this in the next class. What is the primary purpose of pre-processing in ERP analysis?
Filtering.
Filtering out non-neural responses. It is important to distinguish neural responses from artifacts in recorded biopotential. Like there can be other signals also that don't have to be part of our analysis. What technique is commonly used to check electrode contact during EEG recording? Impedance measurement, voltage
Impedance.
impedance measurement. And now, have you ever, like any one of you, have you ever uh, got EEG done?
No, sir.
No, okay. Have you ever seen EEG? Anyone?
No,
No,
sir.
no.
No. So, like, what I know that they apply some
Gel.
conductive gel. Yeah. Even I have not seen that being done. Okay, so they apply some conductive gel, and that is to decrease the impedance so that the signals can have good signal to noise ratio. Okay. So next in the next class we will cover the event related potential. The class will be on 18th April, 6 p.m. The Meet link will remain the same, and that is our last class. Fine. So I will try to put some like detailed explanation over it, as well as we will try to do some simulation. We will see how it is done, and we will put some questions over it. Fine. Any questions still here?
This exam will be these questions you shown, no? Is there any relation towards exam? Same type of questions will come.
Not necessarily. Like as I said, like I'm not part of that question making of the exam. This I am just covering the topics so that you will have some questions in your mind. So something similar might come, but that fully depends on the course instructor.
So it will be completely MCQ, no?
Uh, Hopefully, because there are no calculations. I think even in the assignments, you might not have got any calculation based questions, right?
Yes, sir.
So
Sir, can
mostly it
you
will be
provide previous year assignment?
uh,
Do you?
the assignments that you are getting is the same.
Okay, sir.
This year and previous year same.
Okay, sir.
So not an issue. Okay. So that's all. Let's meet in the next class.
Because,
Next,
on Thursday, we have
yeah,
some.
Thursday,
I
day
have
after
other
tomorrow.
class on Thursday. What is the
Not
time,
an
sir?
same 6 p.m.
PM. Okay. Okay.
No, not an issue. You can have the recording. We'll have the recording, right?
Okay. Okay.
Yeah.
We'll try
So
to come, sir.
yeah, sure. Whenever you are available, you can join.